In this video, we want to prove that singular homology satisfies the dimension axiom. And actually, it's going to be a pretty short video because among the four axioms, Eilenberg-Steenrod axioms of singular homology, the dimension axiom is by far the easiest to prove. So let me write the statement. Well, the statement is singular homology does satisfy the dimension axiom. And let's just recall what this meant. It means that if I take the singular homology, the nth singular homology of a point, so of a topological space which consists of one point only, then this is actually just 0 unless n is equal to 0. So it's 0 if n is not equal to 0. Okay, so what's the proof? Well, the proof is something which you should never try at home, at least in this particular case. Yeah? We just compute the homology by looking at the singular chain complex. And why does this work in this particular case, even though singular chain complexes can be so vastly singular different? Well, it works because the space consists of only one point, yeah? Which has the effect that there's only one map. I mean, only one continuous, but actually only one map at all from the n simplex to the point. So this is the first observation. There is only one map from delta n to the point. And this applies for all n. Yeah? This doesn't matter which dimension we're in here. So in fancy terms, the point is a terminal object in the category of topological spaces, but it just means there's one map into the point for every n here. And this is why the singular chain complex looks like this. Therefore, the singular chain complex of the point looks like, now let's draw it. So remember, the nth singular chain group just consists of all continuous maps from delta n to the point. In this case, that's only one. Yeah. Sorry, this is the basis of the nth singular chain group. So there's only one basis element here, which means the singular chain complex just consists of z's. Yeah. So we've got z in degree 0. Yeah. Maybe I should draw this a little more downwards to have some space. And we have a z in degree 1, a z in degree 2, a z in degree 3, a z in degree 4, and so on. Yeah, so just to make sure we know where we are, let's put down the degrees here. This is 0, this is 1, this is 2, this is 3, and this is 4. And the only question is, what are those arrows? Yeah, so how do the differentials in this chain complex look like? And
so every copy of C is generated by this one simplex in the respective degree.
It's the free Z module generated by a single element, by just this one map, exactly. Yeah. So what are the differentials here? Well, let's just compute it, just by stupidly applying the definition. So if I've got a singular n simplex here, which remember is just this very map, which sends everything to a point, then, well, what was the definition? I need to take this alternating sum here, I equals 0 to n. I've got the sign here. And now this business started here where we took the face or the restriction of the singular simplex to the face, to the ith face. But I don't even have to think about what comes out here, because I do know that what's written here in the end is an n-1 simplex. And there is only one such n-1 simplex, so there's no need to even think here. It is this very only n-1 simplex. This is what it is. Right? And now we see here an alternating sum And the result only depends whether there are odd or even many summons here. Yeah? So actually, if there are even many summons, then all these summons will cancel out because there are as many with +1 sign as there are with -1 sign. And in the other case, well, there will just remain one of these singular n-1 simplices. So this is either just sigma n-1 in case there are odd many summons, which means that n must be even because we start counting at 0. And in the other case, if n is odd, this is just 0. This is just 0, right? So therefore, we see that at all even spots, this differential is the identity. So this one is the identity. This one is the identity. And at all odd degrees, this differential is just the 0 homomorphism. Well, this is the 0 homomorphism anyway, because it ends up in 0. And now I think actually this can already be stated that this is the proof of the dimension axiom. Why? Well, let's just look at it. Say at an even degree, what's the homology at this point? Well, we've got the identity morphism here. What's the kernel of this identity morphism? Well, it's just 0. Yeah? So homology is the kernel of this morphism, modulo whatever, doesn't matter. The kernel is already 0, so the homology will be 0. And at all odd degrees, the situation is the same as, for example, here in the 3rd degree. What's there? What's going on there? Well, the homomorphism here is just the 0 homomorphism, which means the kernel is everything, the whole module Z here, but so is the image of the previous morphism here, because it's the identity morphism. So what comes out here as homology is the quotient of Z by Z, which is the trivial Z module just like in the other case. So in other words, at all these spots here, the homology that comes out is 0, and the only difference is here in degree 0, where something else might happen, but it's not the statement of the dimension axiom to figure out what happens there. Yeah? We can do it anyway if we want. So the kernel will be everything here, the image will be nothing, so actually the zeroth homology is just Z. Yeah? But the statement was only that it's not, that it's 0 at all the other degrees.